various radionuclides need to be determined for characterization purposes during several activities regarding nuclear safeguards and nuclear applications. The different nature of such radionuclides needs to adopt a suitable procedure for their determination. Easy-to-measure radionuclides could be directly measured by a non-destructive analysis, while hard-to-measure radionuclides require a proper sample treatment aiming at destroying the matrix and separating the interfering radionuclides, then a destructive analysis. The separation methods based on the principles of precipitation, co-precipitation, solvent extraction, ion exchange and extraction chromatography focus on obtaining the target radioisotope separated in high radiochemical purity into a homogeneous phase suitable for counting. Unfortunately, radioisotopes concentration into a matrix can be very low, down to some millibecquerel per kilogram. Activity values of 1 becquerel correspond to a very low mass amount of the radioisotope in the matrix, according to its half-life. For example, 1 becquerel of uranium-238 corresponds to a concentration of about 80 micrograms. The same activity concentration of neptunium-237, having an half-life 3 orders of magnitude smaller, correspond to 28 nanograms. Therefore, you can easily understand how some steps of a destructive analysis can lead to losses or contaminations. How could we avoid errors in destructive analysis for hard-to-measure determination? For example, standardized procedure easily enable to avoid external contamination of the sample. Other approaches could be adopted to avoid or check radionuclide losses during the whole analytical procedure. The suitable sample storage in plastic labware, as well as acidification of liquid samples, enable to avoid radionuclide losses because of absorption or hydrolysis phenomena in the first step of the analysis. For the same purpose, a stable or radioactive compound with the same chemical behavior of the target radionuclide could be added to the sample in a suitable known amount. The former is called carrier, and it could be isotopic or non-isotopic. The latter is named tracer. For example, if the target radionuclide is iodine-129 as iodide anion, an isotopic carrier is iodine-127 as potassium iodide, but not potassium iodate, due to the different chemical behavior of iodine in the iodide and iodate forms. Potassium bromide, instead, could be a suitable non-isotopic carrier, and potassium iodide 125 could be used as a radioactive tracer. By evaluating the tracer activity or the carrier concentration at the end of the procedure, it is possible to calculate the effective recovery of the target radionuclide. This is the so-called chemical recovery yield, defined as the ratio between the amount obtained after the separation with respect to the initially added one. Once the target radioisotope has been separated and it is available in homogeneous phase, the counting source has to be properly prepared to be measured by the most suitable radiometric technique. If the target radionuclide is an alpha emitter, the radiometric technique of choice is alpha spectrometry. The sample solution has to undergo an electrodeposition process that enables to obtain a thin coherent coating on a stainless steel planchet. Alpha particles are not self-absorbed in the layer and can be detected by a semiconductor detector under proper vacuum conditions. Similarly, radionuclides that decay by electron capture can be determined by suitable high-purity germanium detectors measuring their characteristic X-rays. Since the energy of these X-rays is at maximum up to tens of kilo-electron-volt, it is necessary to prepare thin layer samples, for example by evaporation, to prevent self-absorption and to improve their measurement. In the case of beta-emitting radionuclides, they can be measured by liquid scintillation counting. The solution obtained from the separation steps is mixed in a vial with a suitable liquid scintillation cocktail. The radiations emitted by the radionuclide dissolved in the cocktail induce the emission of light that is converted into suitable electric pulses and detected. Beta emitters can be measured also by proportional counters, by evaporating the sample solution on a sample holder. However, unlike liquid scintillation counting, proportional counters suffer more severely of self-absorption issues. Whatever the radiometric technique is selected, in order to quantitatively assess the radionuclide concentration in the sample, the instrument has to be calibrated, employing suitable certified radioactive standard sources. For example, the alpha spectrometer needs energy calibration by means of a certified source containing several alpha emitters. Standard alpha sources with known activities are used to evaluate the counting efficiency at different energies. This is defined as the ratio between the counts and the decay events in the time unit. In the case of liquid scintillation counting, the detection efficiency could be affected by quenching. To overcome this point, a series of standard solutions with a known activity of the beta emitter and different quenching levels could be measured to evaluate the efficiency as a function of this parameter. To be able to evaluate an activity that can be interpreted as meaning activity, the background count rate has to be determined by measuring suitable blank sample. In general, since the random nature of radioactive decay, it is important to collect a suitable number of events to have a measurement with statistical significance. Furthermore, counting time has to enable to achieve the minimum detectable activity, which is the level of activity which is practically achievable by an overall measurement method. The minimum detectable activity reflects not only the instrument characteristic, such as the background and the efficiency, but also other factors which influence the measurement, such as the amount of the sample analyzed, the chemical yield, and the measuring time. In recent years, mass spectrometry has become more and more popular in the determination of long-lived radionuclides, and isotopic ratios in the trace and ultra-trace concentration level. Mass spectrometry enables a fast sample preparation consisting in a simple dilution by ultra-pure reagents. The use of ultra-pure reagents assures to reduce the background contribution. Because of the high sensitivity, short analysis time, and relatively easy operation, mass spectrometry has been widely used for the determination of isotopes of uranium, thorium, and plutonium in environmental and waste samples. In this lecture, you have discovered the main issues you have to take care while performing the determination of hard-to-measure radionuclides in a matrix. In particular, the critical aspects of the radiochemical separations, source preparation for counting, and radiometric measurement and techniques have been discussed.